Swayam Prabha. Digital India. Educated India.
Hello, welcome to the first part of lecture 12. In this part, we will be continuing our discussions on the various passive devices. We had already started with one passive device in the lecture 11, which was the multi-section transformer. So in this lecture, we will be starting first with one-port microwave devices, then moving on to two-port microwave devices, and then to three-port microwave devices. Four-port microwave devices, which are called couplers, will be covered in a different lecture. So when I say microwave devices, these are passive. When I say passive microwave devices, so these are devices which have distributed components, that is either transmission line sections or open stub or shorted stub elements in them. So what are these one-port devices? Uh, let's start, as I said, we'll first start with one-port device. So when I say a one-port device, first of all, the S parameter matrix of a one-port device will simply be equal to, will have only one element, which is S11. Okay, so one-port device is just like that. Okay, so first thing is the second is, second point to note is that since there are only one S parameter, there is only one S parameter for a one-port device. So by default, isn't it? This is always true. Hence, this implies that all one-port devices are reciprocal. The third point to note is, if the device is also lossless, then recall we have S transpose equal to U. So this is S conjugate transpose. So this translates to S11 modulus square is equal to 1. So this implies mod S11 equal to 1. So if the device is lossless, then this condition has to be satisfied. So what are these some of these one port devices. Examples are examples of one port devices is, some of them we have already seen. For example, a open stub, then matched load, then shorted stub. These are all examples of one port devices. So these we have already seen, right? We have seen what is an open stub, we have seen what is a matched load, what is a shorted stub. Now here we will actually see how they can actually be made actually. So for that, let me go to my slides. So here you can see that this is, for example, an example of a shorted load. So this is a coaxial cable. So we have the central conductor here, this one, and this is the outer conductor. And what we have done here is simply connected the central conductor to the outer conductor. Okay, but then this is a example of a poor short, because here only this part is connected to the outer cylinder. But then for uniform load, we need all the parts to be connected to the all the parts of the inner conductor to be connected to the outer conductor. And that is what is done here. Here, instead of just one single short between the inner and outer conductor, we have a sort of disc connecting the inner and outer conductors. Okay, so then the next example is that of an open termination. Now, open termination is sort of difficult because at high frequencies there will be inevitably radiative losses. So one way to obtain a good open load is to simply extend the outer conductor. So here see this outer conductor, it's slightly extended. This way the capacitance between this inner and outer conductor is reduced. Also, the radiative losses are reduced this way. Now next is about how about making a matched load. So matched load means there is so for example, the inner conductor here in this coaxial cable should see a load of say 50 ohm or 100 ohm or whatever is my characteristic impedance. So this is somewhat similar to the shorted stub, except that in a shorted stub we want the impedance seen by the inner conductor to be 0. Here it's not 0 but some finite value like 50 ohm or 100 ohm. So what is done is the end portion of this inner conductor is made with some high resistance material to introduce some finite resistance like 50 or 100 ohms, and then the remaining part is shorted. Okay, but this is not a good way, because in microwave engineering, anytime there are sharp edges or sharp turns like here, this inner conductor directly connects to the disk, which is not a good uh, design process in microwave engineering, because anytime there is a sharp edge or abrupt change, that will cause reflections. So what instead is done is that we have this load, instead of having a very straight, very cylindrical load, we have sort of like a tapered load here. So this inner conductor sort of gradually its radius increases till it meets the disc, the base disc here. And this tapered region is actually the load. This tapered region is designed in such a way that it provides the required matched load. So this is how we can implement matched load. And then this is a similar implementation in waveguides. So the previous one, that coaxial cable, was for TEM mode. This is for TE and TM mode. So once again, this part consists of a solid load region, solid high resistance material, which causes attenuation of the electromagnetic wave. So by so we have to now understand, we have to, the definition of impedance for this waveguide, recall, is the ratio of the electric to the magnetic field. So when I say load, it will mean a circuit or some component which causes reduction in the magnitude of the electric field, and that component is this wedge shape. Why do we use a wedge shape? The same logic as why we used a tapered load in the previous case, in the case of the coaxial cable. Similarly, here also we have a tapered load. This is a wedge implementation, this is a spike implementation. Okay, so that was all about one port devices. Please go through your notes carefully. We will, all these diagrams are there in your notes. In the next part, we will be covering the two-port devices. Welcome to part 2 of lecture 12. So in the previous part, we covered the one-port devices. In this part, we will be covering the two-port devices. So let me first, before discussing the various two-port devices, I would just like to recap the properties of a two-port device. Recall that the S parameter matrix of a two-port device will be like this. Okay, and if the device is, so there are 4 S parameters, which implies 8 unknowns. Okay, if it is reciprocal, then my S parameter matrix will be like this. So these two elements will be the same, that is, this element and this element will be the same, and so we have now 6 unknowns. Okay. Two network is lossless, then we have the unitary condition. So if the two-port network is lossless, then the unitary condition conjugate transpose will be equal to U, and then using this condition we know that this condition along with the reciprocity condition, we know that we need 3 unknowns only, where this theta 1 is the angle of S11, theta 2 is the angle of S22, and S11 magnitude. So if we know just these 3 unknowns, then we can find out all the other S parameters. For this chapter or this lecture, we will be considering the following two-port devices: bends, discontinuities, transitions. So like coaxial to microstrip, coaxial to waveguide, and so on. Then we have attenuators, and mode suppressors. Okay, so let us take up each of these one by one. So first, let us consider a bend. For this, I'll go to my slides. So consider these two. These are the two types of bend that are commonly used. First is the radial bend, and the second is the metered bend. So a bend cannot just be, just a simple, say, a horizontal line meeting a vertical line, because that will involve sharp edges, which in turn will cause spurious waves to emit. Anytime there is sharp edges, such spurious waves are created. So we always want the bends to be smooth. So one way is to have this radial bend. In this radial bend, this bend is basically a part of a circle having radius capital R, and the R value should be much larger than 3 times the width of the transmission line or the microstrip line, or whichever waveguide we are using. So here this one is coming horizontally here. It is then undergoing a smooth transition before becoming vertical. Now the same can also be implemented using what is known as a metered bend. So in a metered bend, you have this horizontal section meeting the vertical section. Now they don't follow a perfect corner. Instead of being a sharp corner, the edge of the corner is chopped off, and we have a structure like this. And the rule of thumb is that we have this A value here, small a value, is around 1.8 times the width of the transmission line. So that is the rule of thumb. Now, the next two-port network that we discussed was discontinuities, and here we have examples of such discontinuities. So here, see this part, this yellow part, this is thicker than this part, and this acts as a sort of transition between a microstrip line that has this smaller width and a microstrip line that has this broader width. So the model for this structure, so this is an in-between two transmission lines, one having narrower width, the other having wider width, and its equivalent structure is like this. Okay, now these capacitance is actually the capacitance between this junction of the two transmission lines and the outer conductor. Similarly, when we have, say, a two-port network, which basically forms a gap between two transmission lines. So here the equivalent structure is like this, as shown here. Now the capacitance between the two microstrip lines, this one, is represented by this capacitance, and then the shunt capacitances from these two transmission lines to the outer conductor are shown by these capacitances and are represented here. Okay, so now one more thing, if I come back to this structure, note that the characteristic impedances on this end is different from the characteristic impedance at this end. And that's why the values of these inductors are different. But here in this case, for a gap, if the width of the microstrip line on either side is the same, Then the characteristic impedance on the left side is same as the characteristic impedance on the right side. So the next type of two-port network, or I should say, continuing the discussion on discontinuities as applicable for waveguides. Now, waveguides, as you know, don't have a two-conductor system. There is a single conductor system. But even in a waveguide, we can have these discontinuities, or we can introduce inductance, uh, shunt inductance and shunt capacitance. These are equivalent. So if we want to say model a waveguide as a transmission line and have a shunt inductance or a shunt capacitance, then we can do it this way. If we introduce strips, metallic strips from the between the broader edges, okay, like this, then the equivalent model of that waveguide becomes like this, with as if there is an inductance in shunt. On the other hand, if we introduce metallic strips between the narrower edges, then our equivalent model is like this, and as if we have a shunt capacitance. If we have both, that is this vertical as well as these horizontal strips as shown here, then we can design a resonator. Now these discontinuities can also be modeled for two different like just like this one, where we had this discontinuity connecting two different transmission lines with two different characteristic impedance. Similarly, even in for waveguides, we can have discontinuities which connect two different waveguides having two different characteristic impedances. So one way to do the discontinuity, to achieve the discontinuity, is by this method. So here we have two waveguides sections connected like this, and the equivalent model can be shown to be like this. Similarly, if we have two waveguides connected like this, then we can also show that the equivalent model is like this. Okay, the next two-port network is what we call transitions. That is, they connect, one kind of waveguide, or I should say, yeah, one kind of waveguide to another kind of waveguide. For example, in a SML launcher, which is a very commonly used device for antenna design or filter design. So these launchers are basically the connectors or the interface between the microstrip board and the coaxial cable. These are commonly available. We have them in our labs and they're available in market. So as we know, in a microstrip line, the mode of transmission is quasi-TEM, whereas in a launcher, which can also be modeled as a coaxial cable, the mode is pure TEM. So here, this launcher is an interface between a coaxial cable and a microstrip line, and its equivalent model can be given like this. Okay, and if we are designing the filter or this structure for achieving minimum VSWR as per the Butterworth prototype function, then we get a value of L like this. Okay, this is another type of transition. Now, while the previous one was from TEM to quasi-TEM, where both the waveguides were two conductor waveguides, here the coaxial, so this is the coaxial cable that is coming, and this is my waveguide. So here, this I had discussed many lectures back, but I'll still again discuss. So in a coaxial cable, the electric fields are radial, whereas the magnetic fields are concentric about the central conductor. Now, this is connected at a distance from the end of the waveguide, usually at a electrical length of pi by 2. Why it is pi by 2, it will become clear. But note how the electric fields change. Okay, so they were radial for this coaxial cable, and then as they enter the waveguide, they start their directions change. These dotted lines. So these dotted lines are the electric fields, and you can see after some distance they become vertical. So it's like a TE. So it was a TEM wave in this coaxial cable. Now it has become a TE wave. The magnetic fields, which were concentric here, continue to maintain their sense here. And as we know, for a TE mode, the electric field is perpendicular to the direction of propagation, which is this way. So this is the direction of propagation. But the magnetic fields are planar, and that is what we see here. Now, the reason for keeping this launcher at a distance of pi by 2 from this end is because if suppose some waves travel this way towards right, then they will undergo reflection. When they undergo reflection, there's a phase change of pi, and then twice traveling the electric length of pi by 2 will introduce another pi phase difference, so that total phase difference is pi due to twice first going from here to here and then again coming back from here, from this end to here, and then another pi phase shift because of this reflection, so that the waves have a total phase shift of 2 pi when they are reflected and come back to this end. So that way, the phase of the reflected wave and the phase of this wave that is traveling this way remains the same. Now, the next kind of two-port network which I want to discuss, let me go back to my what is known as an attenuator. So for an ideal attenuator, say the S parameter matrix is like this. Okay. First of all, the input and output ports are well matched. So we have S11, S22 equal to 0. Okay. And insertion loss, there's a quantity called insertion loss, L, which is given by so the output power at port 2, if we draw the two-port network, this parameter matrix is like this. Okay, and this is given as so this is equivalent to our gain term. Recall the transducer gain that we discussed, and recall I had mentioned that if the input and output terminals are well matched, then the gain is simply equal to this term, S21 magnitude square. So how to achieve that? So here, instead of a gain, we have there is no gain, there is decrease in power. So P2, this quantity is lesser than this quantity. S21 will be actually S21 will actually magnitude will actually be less than 1. So the reason of taking this negative sign is that overall this term remains positive. Okay. So now let me show you how to do this. So here, say this is my waveguide and say this is my TE mode. And if I introduce a card like this is just a conductor placed within the waveguide, and we can have, this will cause some loss of power, and because the shape of the card is same as that of the shape of the EM wave, the sinusoidal EM wave. So again, we have a smooth surface which will not introduce any spurious reflections. And so that's why our matching will be achieved because of the shape. Now we can also have a resistive attenuator for TEM mode. So there are two basic circuits. One is this T network and the other is this pi network. And suppose alpha is my attenuation factor. By the way, alpha is equal to modulus of S21 square. Say we are given a certain value alpha, how do we design this R1 and R2? So it is given in Poser. The value that you will obtain is given as R1 and R2. And if you use this model, then G1 and G2 values are given like this. I urge you to go through this derivation given in Poser. So one thing I would like to say about attenuators is that attenuators are well known. Any resistor placed in a circuit is an attenuator. But here, in addition to providing power loss, we also have to ensure matching. So that is what is different from just adding a resistance in a circuit. Here, matching also has to be achieved. Coming to the next type of two-port network. So these are what are known as mode converters. So here I'll show you two of these mode converters. In the first one, we have a cylindrical waveguide with concentric metallic wires placed like this. And in the other one here, this one, we have radial metallic wires placed like this. Now, when you place a concentric metallic wires like this, what happens is the tangential component of the electric field vanishes. So what happens here actually is that it can be shown that TE01 modes cannot exist when the tangential component of the electric field vanishes. You can see it. You can go through the derivations for the TE01 mode. You can see the equations for the TE01 mode and prove that if ET, that is the tangential component of electric field, is 0, then the TE01 mode will not exist. It will be basically reflected back. The power will be reflected back. Similarly, it can be shown that if the radial component of the electric field vanishes, then the TM01 mode will not exist. You can again prove this from the equations for the TM01 mode. So there are some more two-port devices. Some of them we have already covered. Impedance matching network, we call the multi-section transformers. And then there are some which we will cover later, which are, for example, the resonators and filters. So with this, we come to an end to this part. In the next part, I'll be covering three-port network of lecture 12. So in this part, we'll be covering three-port devices. So we'll be proceeding just like we proceeded for one-port and two-port devices, where we will be analyzing the S parameters of the three-port network for various cases like lossless, reciprocal, and so on. So let me once again share my screen. So for a three-port network, the S parameter matrix will be something like this. So if this network is lossless and reciprocal, then first of all, for reciprocity, we have to have S will be equal to its transpose. So then S parameter matrix should be like this. Okay, and then so this is for reciprocal. Now in addition, say it is also matched at all ports. Then we have conjugate transports is equal to the identity matrix. So if sorry, I just made a mistake. If matched at all ports, then we have S11 is equal to S22 is equal to S33 is equal to 0. Please note this change. And if also lossless, then it implies okay the unitary condition. Okay, so with these in mind, let us try to evaluate the S parameter matrix. So let me clear the canvas. Okay, so for the for the system to be 3-port network to be lossless, reciprocal, and also matched at all ports, we have to have okay. So now if we apply the unitary condition for it being lossless to this matrix, what do we get? We get the following equations. And we also, so these are the, okay, these are first three equations, and we also get some other equations like S12, S23 conjugate is equal to S12 conjugate S13 is equal to S